Hey everyone, we have another DOS assembly video for you. Now this is going to be a long format video, which means it's not going to be fast paced, it probably won't be super duper exciting. It's an opportunity for you and me to hang out, to crack open a drink, maybe eat some popcorn and learn something. So that's going to be the goal. If you're looking for a quick dopamine fix by watching someone go skydiving without a parachute or something, you're not going to get that rush that you would from watching that video. But if you just want to hang out, got nothing better to do, you want to learn something and you want to get into some greater depth on DOS assembly, you're in the right place. If you like this type of content, this long format, this is a little bit newer for me. A couple years ago, I did have a video that was a long format, but not going to be as long as this will be. So if you do like this, please hit that like button. It lets me know that you like this type of content. And then if you like the content in general that you see on the channel, please hit subscribe. It lets others know that this content exists based on your viewing preferences. So the first thing we need to consider is that when we run a program, everything is in the memory, and it's dealing with working with the memory itself. So when you stick that floppy disk in your computer and you run your program, it is not actually going to be running the program on the floppy disk. What it will do is it will copy the entire program off the floppy disk, put it into memory, and then that's where it actually lives, is in memory. And we'll get into memory a little bit more here shortly. I have up there, though, that the registers, we also use those, but they're not in the memory, but they actually are memory themselves. So let's discuss that a little bit. Let's draw our friend a computer chip here using a very sophisticated program. You might recognize the Microsoft equivalent. All right, so let's just put, I don't know, these are all perfectly evenly spaced, as you can see. But anyway, there's our computer chip. Now, using copper wires, one of the things that it'll be connected to is a memory controller. And DOS is a 16-bit operating system, which means that we are dealing with 16-bit memory. Technically, it's 20-bit because of memory segmentation, but we're not going to get into that. We're going to pretend that segments don't exist for right now and that it truly is 16-bit, which means 16 of these little wires will run over to the memory controller. Now you might be thinking, well, what is 16-bit and how can a wire that carries a voltage get me memory? Well, first let's picture memory itself. Memory is kind of like a locker room. If somebody says that their baseball glove is in locker 263, you need to find the locker that says 263 on it, and when you open it up, that's what you're looking for. And memory is the same way. Now with gigabytes and terabytes of information, there are literally millions and trillions of these little lockers, but we're in a much simpler era of computer science here. Everything is 16-bit, which means that the lockers can only be so large until we run out of numbers to put on our lockers. So let's look a little bit first at some number theory to explain how these numbers all kind of relate to one another. So you can see we're using 16-bit because it's a 16-bit environment we're in. Let's start with a normal number that we'd recognize in decimal. We have 1, 2, 3, 4. Well, the neat thing about this is the symbols that we can use are 0 through 9. They're actually in base 10, which decimal is base 10. There is no symbol for 10. So we have to go to the tens place and then put the 1 symbol here and a 0 symbol here. And the same thing happens when we hit 99. There are no more symbols for the tens place. We have to go to the hundreds place. And let's break this number down into its parts. So 1, 2, 3, 4 actually is equivalent to 1 times 10 to the third power. And if this looks like this is just madness, don't worry, we'll explain it. And it will make perfect sense by the time we're done. And then you can tell all your friends how much of a genius you are, that you understand how the math that you do on a normal basis in your life makes perfect sense, right? So let's start way over here. 10 to the 0th power, well, actually, any number to the 0th power is the number 1. So this turns into the number 1. 4 times 1 is the number 4. So that's easy enough. Now 10 to the 1st power is 10, because, well, it is. And 3 times 10 is 30. So we're making progress. What about 10 to the 2nd power? Well, that's the same as 10 times 10, which is 100. And 2 times 100 is 200. And then after that, we have 3 to the 3rd power, which is 10 times 10 is 100, times another 10 is 1,000. And an easy way to do this actually is look at this number, and that's how many zeros you have. So 1 times 1,000 is 1,000. Well, if you take 1,000 plus 200 plus 30 plus 4, you get 1,234. And that is pretty straightforward. You probably never realized you were doing that, but there you go. Well, binary is kind of the same way. Let's look at something called a nibble, which is 4 bits. Yep, whoever did it, they were creative, because half of a byte, spelt with a Y, is a nibble. Also often spelt with a Y. So let's look at this number. What is this number in decimal, the number system that we're used to using? Well, before we do that, let's count first. So this is the number 0, and this is the number 1. But we ran out of symbols, because just as base 10 doesn't have a symbol for 10, it ends at 9, there is no symbol in base 2 for the number 2. So we have to go over to the 2's place. And then we have 3. And then we ran out of symbols again, so we have to go to the 4's place. And it's just kind of like the 99 goes to 100 situation, and so on and so forth. And there we go. That's how we count in binary. Fancy, right? So what is this number? Well, let's break it down like we did above. 1 times 2 to the 3rd power, because this time we're dealing with binary rather than decimal. 0 times 2 to the 2nd power. 1 times 2 to the 1st power. And 0 times 2 to the 0th power. Again, 2 to the 0th power is the number 1. 0 times 1 happens to be 0. After that, we have 2 to the 1st power, so 2. 1 times 2 is indeed 2. And I suppose we can clean it up like we did before. 2 times 2. Well, that's a hard number, but it does come out to be 4, and 0 times 4 happens to come out to 0. And then we have 2 to the 3rd power. 2 times 2 is 4, times another 2 is 8. So we have 8 here, because 1 times 8 is 8. All right, so 8 plus 2 is 10. All right, so this is going to be the number 10 in binary. Yes. Feels like I'm saying something wrong, because it feels like this should be a much larger number, doesn't it? But no, indeed, 8 plus 2 is 10. All right, so the other thing you probably heard about is hexadecimal. And hexadecimal is used all over in assembly. You are going to be using hexadecimal a lot. Why do you do that? Well, decimal, unfortunately, is not convenient to work with in computer science, because computers use binary. However, can you imagine typing out all these ones and zeros? That would be a nightmare. So computer scientists figured out hexadecimal will work better for us. And let's look at counting first, just like we did previously. So we have 0 through 9, which gives us all the numbers, but in this case, it's base 16. So we need to have a symbol to represent the number 10. And they picked letter A, and then 11's B, C, D, E, F is 15. And after you get to F, now finally we hit the base number, which means that 10 is the number 16 in hexadecimal. Now you might be thinking, well, why is this convenient? Well, the reason for that is one of these digits, or one of these symbols, however you want to term it, represents an entire nibble, which means a byte is 2 nibbles. So let's look at this, for example. This is a byte. Well, what byte is it? Well, let's look at what it equals. So we have A, which happens to be the number 10 in decimal, times 16 to the first power. And then we have 3 times 16, again, to the 0th power. Now, in this case, let's start over here again. 16 to the 0th power is 1. So 3 times 1, last time I checked, was 3. And then we have 16 to the first power, which is 16. And 10 times 16 is 160. So this gives us a total of 163. So this byte is 163. Now, this is very helpful because when we assemble this program, what it's doing is converting it into binary for us. But we don't want to see all ones and zeros because, well, we'd probably give ourselves a headache and it would fill up the entire screen with a lot of data that doesn't mean a whole lot to us. However, this is more helpful. So let's look at the hexadecimal for this program we made. So the program actually does start here, where we're moving the number 9 into AH. So a way of putting this is like this, in like a C-style language. It would say AH equals 9. What is AH? Well, don't worry about that quite yet. We'll cover that very soon. When we look at the binary, we can see that we have lots of bytes. Again, these are hexadecimal characters, and 2 of them is a byte. Now, we notice that we have B4, and then we have 09. Well, what's happening here is this is B4, and this is 09. And you might be wondering, well, how can a number mean move a value into this register? How does it know that it's not a number? How does it know that it's supposed to be a command? And it comes down to the location of things. For instance, if I said I was going to store my computer at the store, how do you know that the first time I use the word store that I mean put it into a location, and the second time I use it, I am using it as a location? Basically, the first time it's a verb, and the second time it's a noun. Well, computers are the same way. If they see a number and they are not currently running a command, they assume that that number is a verb, it's a command. So in this case, B4 means move this value into H. Now, let's do something creative. This is going to be gibberish kind of to the computer. There's not a command like this. But let's say we want to move the number B4 into AH. Can you guess what's going to happen? We have B4, B4. So again, B4 means move something into AH, and this time it says move the number into B4. This would kind of be that example like I used before of I'm going to store my computer in the store. Storing is like B4, and the store is like B4 in this case again. So that's how you can look at these numbers. Let's make it a working program again with the 09. When you look at these programs, that's what you have to do. And obviously you have to keep track. There are no periods at the end of your sentences. So B409 means move 9 into AH. And then after that, we have BA, which is move something into DX. But in this case, it's actually going to be moving this entire word, which is 2 bytes. So you have to keep track of where you are in your program. And fortunately, assembly does that kind of for you using these labels. Anyway, I'm getting ahead of myself. What about these registers? We've talked about these a little bit, but we haven't explained exactly what they are. So let's go to our handy drawing again. And these registers actually live inside the CPU itself. And they're basically like global variables. Now, the first time you programmed, you probably ran across global variables. And if you're anything like me, before you realized the implications, you thought they were the coolest thing ever. You create them once, you use them indefinitely, you don't have to worry about them going out of scope and no longer being valid. And then you realize, but I have to keep track of every single thing that goes into that variable, because if I change it and I don't remember I changed it, it doesn't have the value I remember was in there, right? Sound confusing? Yeah, that's because it can get that way. So what is AH and DX and all these different things? Well, inside the computer, it stores words. Again, it's 16 bits. So each register holds 16 bits. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, well, we'll keep the nibbles together. There we go. There we go. Now we have 1 byte and 2 bytes. And as you can imagine, sometimes you only care about 1 byte. In this case, AH, we only care about the high byte. So if we look at this, this is AH and this is AL. So this is the high byte for A and this is the low byte for A. There's also its friends BX, CX, and DX. So often these are used for very specific things, like this is generally used for math, this is used for keeping track of places in memory, this is used for counting, this is used for holding data or whatever. But in the long run, you can kind of use them for whatever you want. They're called general purpose registers because you can use them for general purposes. So we're storing the number 9 into AH, which we're going to change this into hexadecimal. Oh, look at that. I can actually read that. And AL is going to be, well, it could be anything. We kind of don't know what AL is at this point. It could be any sort of number because we're not specifically setting it to anything. So it's going to be whatever the computer set it to. But what are interrupts? That's the next thing, because the reason we set this into AH is because we're calling interrupt 21. And the reason for that is if we look at the interweb here, we have function 09. Yep, it goes into AH. And then when you call interrupt 21, which is the category we're under, interrupt 21 functions, it will display a string for us. So when you work with C or other languages, all of your functions have names, right? You call puts to put stuff on the screen in C, or you might do printf, and then you have to pass in the parameters, and the function has a name. It's printf, or it's puts for put string. But we're dealing with numbers here. Everything is a number, basically. And in this case, number 9, function number 9 is display a string. So that you can see there's other things. There is inputs and checking statuses and resetting disks and blah, 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 blah. There's tons of things that you can do. You can set the date. Each function is called by a number. And when you look at this, the number of the function is always set into AH. And that's why we're setting 9 into AH. Now the other thing it says is we're going to ignore DS. That's the segment thing we talked about. We're going to pretend segments don't exist because we're dealing with COM files, and yeah, we're going to pretend that they don't exist right now. DX though. DX has to hold the address of the string that's terminated with a $sign. So like we said, everything is in memory. So what does this hello label do for us? Because we're using it here. We're not actually saying, okay, so the beginning of the program is, let's see, this is 0, this is 1, this is 2, this is 3, and I'm cheating, I'm watching these across the top here. But look at where H starts. H starts at 0C. So why don't I have to put in here dx equals 0C? Well, or I guess it'd just be C in this case. Why don't I have to do that? How can I use this label hello? Well, let's look at this. 0C is right here. So BA actually is getting its 0C value from this label. This label is keeping track of everything for us. Now, I think that's pretty nifty because it's, I don't know, isn't that cool? Isn't that cool that it keeps track of the memory locations for us? Now, I did say that it has to hold an entire word, and you'll notice there's 0C and there's 01. So what number is this? Because it can't be this, because this is a much larger number than just the simple little, let's see, A is 10, 11, 12. This is simple than the number 12 that we're looking for. This is 12 to 16 squared. Yeah, okay. So that's a big number. The reason for that is it's little Endian. And this is crazy. The numbers are stored backwards. So if you wanted to store 1, 2, 3, 4 in memory, it will be stored as 3, 4, 1, 2. Why? Well, it actually does make sense when you look at the architecture itself. And the reason for that is we have this entire word in memory, and the computer is going to be starting on the left and it's going to be moving forward. And this command happens to say, I need an entire word. If it said I only need a byte, instead of going, well, how much is saved here? Oh, there's 2, so I have to skip 1. It just always goes to the next thing. So if instead of a word it was a byte, it would go to 0C. And in the case of a word, it would go, okay, I have 0C and I have 01, and it automatically will flip those. Now that might seem a little confusing, but again, if you had the number like this, we'll pretend these are hexadecimal numbers, even though they look conveniently like decimal numbers, and we said we can store all of this into our memory, we would end up with actually this. And that's great, but I say to you, your variables can't hold 4 bytes. They only can hold 2. Well, what that's called is we're going to be truncating this number. And you have to decide which number is more important to you. Do you care more about this number? So 12, I don't have commas or anything in here. Let's see. 12,034,000 or 340,000, or do you care more about this number, 5,678? And the computer scientists determined that you probably care more about this little number than you do about that giant number, because yeah, they basically decided that for you. So thank you, computer scientists. But what that means is when you want to throw bytes away, you just don't read as far, rather than keeping track of how big it is and then figuring out how many boxes to skip. All right, so that got us more in the weeds than I thought we were going to get into, but hey, we're learning, right? So anyway, you'll notice that this value that it had was 010C. Where did this 01 come from? It came from here. So let's discuss this origin point. Nobody ever talks about the origin point. They say, oh, this tells it where to get stored in memory. And no, it doesn't. Find the number 100 in here anywhere. It is not in here. It doesn't tell it where it's stored in memory. What happens is when your program, which is all of this, is loaded in the memory, DOS will load it at this address. You could put in, if you put in the number 200, well, let's do it and let's see what changes real quick. Let's see if we can watch it refresh. If we make this, it passed. All right, I got to reopen it. Well, that's no fun. But oh, that's why it made a new binary file. Oh, good, we can compare them side by side. I like this even better. Don't you love it when you accidentally do something and it doesn't work the way you want, but then you find out it's better anyway? Let's look at the comparison of these two. So this is the same, this is the same, this is the same, this is the same, and here's the difference. The first one is 100, meaning from our COM file, which is when we had this at 100, and the second one has a 2 in here. So the difference is when it's 200, it's doing this, and when we change this to 100, it is doing this. So what does the origin point do to answer our original question? Our origin point is so that when this knows it's at 0C, it can save the absolute memory address. It knows DOS is going to load this at location 100, and we have to store location 100 and C, so 10C is where this will actually be located in the memory. So that's what we need to store here. Now, how do you keep track of all this? You use labels. Instead of keeping track of this memory, because if we add another command in here, this isn't at 0C anymore. This just got bumped out to, where would that be? 0F? Maybe 10 at this point? Well, yeah, that's a pain. So what do? We use labels. The assembler keeps track of all this for us, and that's what the origin point does, is it figures out this exact memory location by using the origin point plus this offset that's being provided. So what does int21h mean? Well, what it means is that it's basically a built-in DOS list of functions. And we saw that when we looked at this. These are the 21h functions. The way it works internally inside the computer is a little bit of a mystery to some people, so let's draw it out. This is going to be our giant locker room, I guess, and you can imagine that inside our locker room we have all of our lockers, of our memory lockers, blah, 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 blah. Each one of these has an address in it, and each one holds a byte of our information. Okay, so let's clean this up a little bit. At the very beginning of our memory, because remember, we only have so much memory to work with. We only can work with 16-bit, technically 20 bits, but the very beginning of our memory is taken up. Oh, that's not the one I wanted. I wanted this guy. It's taken up with some interrupt tables that the BIOS has. And then there's going to be some more data specific for the BIOS here, and then we're going to start to get into some of the things that like DOS has set aside, whatever else. Our program at some point will actually exist here around 100H, and then we're going to have free memory to be used, and then at the very end, the BIOS, which is the basic input-output system of the chip, is going to use some more. And this is like all the memory we're able to use. Kind of. Some of this memory is reserved, like this might be like the video memory for VGA, so anything you stick in here will instantly appear on your screen. And yeah, that's fun. We will actually show that if you stick with me to the end of this amazingly long video. But if you just start filling this memory location up, it'll start filling up your screen with characters or dots, depending on which mode you're in. All right, so 21H. Well, in the case of our DOS interrupt table, which it's probably not exactly in the right spot, it might actually be after this, but it doesn't matter. The point is there is a table, and the table has the numbers, let's see, 0 through 6C. It looks like, well, there's a few in these that are really large too. But it has this table that says if I see this number in AH, I need to run this function for the user. They want me to do something. So if you started writing an assembly thinking that you were going to write everything by hand and that you weren't going to get any help from anybody else's code, that's not true. We can sort of make it true, and at the end of this video we will get closer to that, but we're not. We are using whoever was sitting at Microsoft back in the 1980s code that wrote in the interrupt 21 group of functions. He wrote the 9th function. We are using his code to say on our screen, hello world. So, yep, you're still using other people's code, but we are understanding a little bit more of how this works, so that's neat. Now you'll notice there's the 4C00. Let's look at what that is real quick. Oh, that's the wrong window. It's not listing it. Was that an int? We're going to close this for now. I don't think we're going to draw anything for a little while. Yeah, it's a 21H. Well, this is letting me down. Oh, no, it's not. 4C00. Just says 4C. Anyway, though, yeah, it means terminate the program. So this is going to be your return 0. And I'm trying to remember off the top of my head. Oh, duh. Let's look at that one real quick. So AL is our exit code. AH is our 4C function. So we're using AX here. Again, remember AX equals AH and AL. So we're setting 4C into AH, 00 into AL. If we set this to 4C01, then we would say that we're exiting with error code number 1. And we want to return 0, you know, like in C, return 0. We want to end that way, not this way. So that's why we have it here. Another way you could express this using more bytes of memory is like this. AH is 4C, AL 00. And I guess that's a benefit of when you don't look at this for a little while and you come back, there's little mysteries that you left behind for yourself to figure out again. So there we go. And is it worth? Yeah, I guess it is. Let's see the difference, because this is some of the beauty of the art of assembly. Let's make this real quick. Let's view it real quick. Actually, well, we can see here it's 25 bytes, but we can see it ends here at 10 and 08. Now let's switch it over to AX. And let's make it again. And it's 24 bytes. and now it's not at 0.8, it's at 0.7. You might wonder, well, what the difference is, and that is when we say move into AX, what we're doing is this is going to be 1. If I can find it for you here real quick. B8 means move into AX, and it's moving again for C 0, 0. Remember that little Endian thing? It's backwards. So when we did it the other way, when we did AH, which as I recall is B4, but let's find out what AL is. Now we have B4 for C, B0, 0, 0. So we saved a byte of data because instead of having to call B0, B8 essentially did both of them for us. It did the AH and the AL. It moved it all into AX. And then we call interrupt 21, and then that hands over control back over to DOS so that DOS can stare at you with this flashing, blinking cursor saying, I'm ready to do whatever you want me to do next. All right, so we've talked about 16-bit memory. We've talked about our origin point. We've talked about how this address is stored into DX, and then we use other people's code to actually display it on the screen. And then we hand a control back over to the DOS operating system with the error code of 00. Now I said we also are going to work with BIOS calls. And we're going to burn up all day on this video. Why not? So that's the beauty of DOS, is it also is able to use BIOS calls. So we're going to have to do a little bit different things now. Let's go to our friendly Wikipedia page and let's look at int10h. And there should be a table for us here. And the first thing we're going to do is we need to set our video mode. And the reason for that is we want to make sure we know exactly what video mode we're in. And if we click on this, does it tell us? Lo and behold, it does. I'm surprised it didn't go to a Wikipedia page, but thank you, Columbia University, for having this saved. What we're going to do is we're going to use video mode 3, which is going to give us 80 characters across the screen, 25 down. So if you played Battleship, you're going to be really good at this. And it also has colors, so that's going to be handy. And it starts at memory address B800, which we do not care about yet. We will when we get into it more. Now, if you think that this looks really handy, all in black and white, you won't like this as much, but if you are a person that slightly likes to see more colors, you can actually go to my website under BIOS programming. We're going to actually probably follow along with the displaying text. So what we need to do first is, actually it's going to be under, not under here, it is under setting the display. It's always the one I click last, right? So the first thing we need to do is set our display. We saw that on that BIOS table, AH was 0 and AL is 3 because that's the mode we wanted. When we look at our video modes here, 3 is 80 by 25. It's a text mode with 16 colors. Ignore the address for now. All right, so let's do that. Let's set our video mode to this, and I'm going to actually just copy and paste. You don't need to see me type something on the screen that already is there. And what we're doing now is we have set our video mode to 3, which technically means we can support color. You won't see that yet, but technically it means that. Instead of int21, which is a DOS interrupt table, we're going to use int10, which is a BIOS interrupt table. So we're going to be using other people's code now to set our video mode to this. And if we go under our displaying text, let's copy this. You can see that the video services, 00 is set your display, and E is display a TTY character. If we go into that, you can see that AH sets the E, AL is whatever character we want. The rest of the stuff we're going to ignore, and there are no returns. So let's do that real quick. So into AH we have E, and then we just have the letter, let's do the letter A, why not? So A is an AL, and we call int 10, and we're going to get rid of the string. It's not applicable at the moment. Let's make this, and let's run it. Oops, something didn't build right. Let's see here. We're going to delete this, make this again, and we have our com file. Did I actually run it before it was able to load it into memory? No. Well, that's magical. What's going on? Oh, I'm using a makefile from a different tutorial. This is the Getting Started tutorial. We're in the parts tutorial, talking about parts of a program. Let's fix that. All right. Control C is the fastest way to kill a program. In the Linux terminal, let's do make run now. There we go. Now we have A at the top of the screen. You can see by changing the display mode, it also clears the screen for us. We don't have that big blue box up here anymore. And then when we return control back over to DOS, we get our C drive with the fast blinking cursor again. Okay. I believe the first video explained this makefile and how that works, so we won't dig into that. We'll just keep digging into our assembly program here. Now, up to this point, you have seen how interrupts work, how registers work, this location, how it works, things like that. Let's start to do things that actually require a little bit more work. Let's display a string. Now, the BIOS doesn't actually have a display string, which is what we were using int21h for. But let's bring back our hello label, and we'll put in here declare byte, and we'll do the bytes for hello world, and this time we'll end it with a 0. You know, in C you have null terminated strings, and that is what this is. When it runs across the actual number 0, not the number letter 0, which when you go to the ASCII table, it makes more sense because the actual number letter 0 is hexadecimal 30. Hexadecimal 0 is null, so that's a null character. Anyway, that's going to be the end of our string. And if we make this real quick, you can see again, we have hello world, and then the very last thing is our null character. Great, so we're going to leave this alone, and what we need to do is we need to find a way to load this letter H into our AL for us. And there is a way to do that, and it's called load string, and then we'll do byte. So we're going to load into AL automatically whatever this address that we're pointing to is. But we're not actually pointing to an address yet, so let's fix that. We need to specify into SI, which is source index, or our string source index. And it calls for an address, and again, it's going to automatically find this address using this label for us. When you do load string byte, it will take H, store that into AL for us, which isn't on the screen anymore. I can't click on anything. Oh yeah, right here. It will do this for us, and then it will automatically increment this to point at the next byte, which happens to be an E. We'll only do this once without the loop, so we should get a letter H on our screen. And we do. So now you're probably thinking, well, let's do a while loop. So the equivalent would be while true. And what we want to do is this will store all of our string stuff, and we want to say something along the lines that if AL happens to equal 0, then we want to break out of our while loop. And then you can infer that the curly braces would be here and there. So what we need to do now is we need to begin basically a while loop. So let's create a label, because that's how you do it. So we'll call this our while loop. And I'm going to tab everything over for my sanity. And at the end, it is a while loop. So let's jump to our while loop. And we have an infinite loop. The problem is it doesn't have this breakout statement. So it literally will just keep on running. Once it gets done with our program, it will just keep running in the RAM more and more until eventually it hits code it has no idea what to do, and it will fault out and the computer will crash. That's always exciting. And then you'll have to reboot your computer, or in this case, DOSBox. So let's not do that. Let's actually remember to break out. And to do that, what we need again is a label. So we'll call this breakout. And yeah, we can do it that way. So the way we do this is AL at this point equals our character. And if our character happens to equal 0, then that's when we want to do stuff. One way to do it is the compare statement. And actually, we will do it this way for now. There are more efficient ways of doing this, but let's just keep it simple. So we're going to compare AL to 0. And the way this works actually behind the scenes is it will take AL minus the second number, and then depending on how the math went, it will store it in the flags register. Now the flags register is a special register that is going to be 16 bits long. I might not have 16 there, but let's be a perfectionist, right? All right, so I don't remember off the top of my head, but one of these, one of the ways you can look at this is it says 1 or a 0, which is very similar to check boxes. So if it's 1, the box is checked. If it's 0, the box is not checked. And these are called flags. One of these is called the 0 flag. And what will happen is if AL minus 0, so in this case, if it is 0, 0 minus 0 equals 0, the 0 flag will be set to 1. We'll pretend it's here. If it's any other number, if it's a 1, 1 minus 0 is not 0, this flag will not be set. It'll be reset over to 0. This honestly is the way we do if statements. So, yep, flags are important. So we're going to set the 0 flag in this case if AL happens to equal 0, because 0 minus 0 equals 0, and that gave us a 0 result. And then what we'll do is we're going to do a jump 0, or if you want it, if you don't care about what it's doing behind the scenes, the equivalent command is jump equals. So if these two things equal one another, jump equals to breakout. And let's get rid of our comments, because now they're just creating clutter. And let's step through this with our mind. So AH equals E. We are, well, yeah, this is a bug. We'll fix it. But we're moving hello into the source. We're loading H into AL, because that's where the source is. We're comparing AL to 0, and H is not 0. So if its jump equals is true, we're going to break out and end our program. If it's not true, we'll keep going, and we will display it on the screen. And then we will jump back to the top, and we'll set our address to hello. So we're here again, and we're going to load an H into there, and it's not 0, and we have an infinite loop that will never ever leave, and it'll just fill the entire screen with H's. So let's fix that. All right, now again, AH is E. We set this to this memory location. It loads H into AL. It's not 0, doesn't break out, displays it, runs to the top. Now it displays the E because it automatically incremented, and it'll keep going until it hits a 0, and then it'll call breakout, and then we'll leave our program. So let's do that real quick. Oh, it's not happy. I deleted this I somehow. There we go. And I knew that because it said something about the number 20 here. Actually, no, I just looked for the only time we called int 21. But the line number is helpful if you call int 21 more than once. All right, let's make run this. Hello world. There we go. So first time we did this, we used DOS interrupts. Second time we used BIOS interrupts. We also introduced you to if statements. If statements. Yeah, well, that's basically what they are. And we introduced you to loops. Let's do this another way before we start getting into direct video memory. Those of you that have thought about this might have thought, okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters long. What if we did a for loop and we just ran this 12 times? Yeah, so let's do that. Let's get rid of our 0 on the end. We actually don't need it in this case. And what we'll do is we're going to create another label. We'll call it length, hello length. And what we're going to do is we're going to store the value. $ means our current address in memory. So let's see, this was 38 bytes long last time we ran it. We got rid of the 0, so I guess 37 bytes. So this will say wherever we are, so byte 37 minus the location of where hello is, and hello is going to be at byte, let's see, 36, 5, 4, 3, 2, 1, 29, 8, 7, 6, 5, 4. So byte 24. So we're at 37 minus 24, and that will tell us the number of how long this string is. Sound complicated? It's not too bad. It's not too bad. Let's make this once and take a look at if it gave us what we're expecting. So in this case, 0C is going to be how long our string is. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I use my goldfish memory here, that's number 12. A is 10, B is 11, C is 12. There we go. That's the length of our string. And the way it did it again is by taking our current memory address, which is 37 at this point because the number 12 is not on the end, minus the location of this, and that happens to be 12. All right, so let's call it our for loop. We're going to use CX. CX is also known as the counting register, and the reason we're using CX and not just CL is we don't know what CH is. CH could be, it could have any number in it, and our loop will run a lot longer than the 12 we're expecting if CH happens to be something like AA or FF. So what we're going to do is we're going to, AH will be 00, that's implicit. We don't need to necessarily say that, but we do want to store in the length of whatever hello length is. So instead of manually typing in the number 12, like I almost did for whatever reason, we'll just put it in there. And I take that back. What we have right now is we've told it the memory location, which is byte 38. So we've put 38 into CX. We don't want to run this loop 38 times. So what we need to do is we need to say, tell us the actual number at hello length, which is the number 12. All right, we no longer need to worry about breaking out. For one, we'll never hit a 0. And then what we do is we use the loop command and our for loop. So let's step through this once and see if it makes sense before we run it. E is in the AH yet again. The source index for our string is at hello. We want to run our loop a total of 12 times. 12 happens to be stored here once this math is done by the assembler for us. And we don't want to know byte location of 38. Actually, technically, it's 0138. So yeah, we don't care about that. That's too large of a number. We're not going to run it that many times. We want to know what number's there, which is the number 12. So we use our little square brackets. We have our loop. We get the letter H. We display it on the screen. And then we say loop command, which basically subtracts 1 from CX. So now we're at 11. And it checks to see if it equals 0. If it equals 0, it keeps running the program. If it does not equal 0, it will loop yet again. So we should get the same results using a for loop. And what's interesting, though, is this is exactly the same number of bytes. So if you thought we were going to save bytes by getting rid of that comparison statement and our jump, we gained it in our saving our counter and saving the length of our string somewhere. A funny little tidbit, but oops. I want to run this, and we get hello world. So this was the for loop example. We just did the while loop example previous to this. Now, instead of doing it this way, let's actually start to work with the memory directly. Yay! So now what we're going to do is we're going to work with storing things into that slot of memory in the window that I closed. But remember how I said if you put anything in memory there, it'll show up on your screen? So let's do that. Again, we'll go to my little tutorial page for BIOS programming. And after staring at a dark screen and then seeing all this white, that definitely hurt the eyes a little bit. But let's see here. We want to do displaying a string. Obviously the BIOS program is a little different origin point. You got some weird magic number stuff happening at the end. If you're going to use this for DOS programming, just disregard this stuff at the bottom and the origin point. The stuff in between is still and this. You're not actually going to halt the processor. You're going to return control back to DOS. So there are some slight differences. So I guess just read the code and don't do anything bad. All right, so this was an example that we actually just did. Huh, look at that. I use almost the same variable names. Huh, at least I'm consistent. Oh no, I did not record how to do it with, yes I did, under colored text, I betcha. Yep, there it is. So we are going to start with, you know what, let's do it. Let's go full color right away. We'll step through it, so it'll be fun. The first thing we need to do now is we actually have to care about segments. So memory segments are an interesting thing with the x86 processor in 16-bit mode. They go away in 32-bit mode, but in 16-bit mode, which is what we're currently using, they are something that we have to consider. The way they work is they're a little loopy, and I do plan on doing a separate video on this, but I guess you guys get the sneak peek premiere special edition. But let's say that you'll see it represented like this: ES and then DI. So remember, this was our source index. DI is our destination index. So basically, rather than pulling stuff out of memory, which is what we're doing here, we're going to be putting stuff using the store string byte into memory. But we have to point to the right memory, and that memory uses the extra segment as well here. So let's just pretend it's A to start out with. So if it was A0000, now remember, each nibble is 4 bits, and this is where that 20-bit memory stuff comes into play. And you might be thinking, okay, so 20 divided by 4 is 5. So we have 1, 2, 3, 4, 5. And we know that our registers can hold a total of 16 bits, which 16 divided by 4 is 4. So it can hold this information. How does it get only 1 when it holds an entire value? And that's where this weird little segment thing comes in, where they multiply it by 16. Now, how does that work? So let's say you have the number 12. If you multiply that by 10 in the decimal system, you get 120. It's the same as moving the decimal place over 1 to the left. Now, the nifty thing is, in binary, if you have the number 2 and you multiply that by the number 2, the base, then what you end up with is the number 4, which is moving the decimal place over 1 to the right. So we multiplied by 10 here, which is base 10. We moved it to the right. We multiplied by 2 here, which is base 2. We move it 1 to the right. Hexadecimal, what they do is they take this number and multiply it by 16, and it creates this new number. It moved the decimal 1 to the right. This is then added to whatever this is. So for an example, we'll pretend that DI happens to equal 3 and ES is A000. Your final memory address that you've been waiting for is A0003. And this allows us to access up to 1 full megabyte of memory, which is almost nothing. But you can see why they did implement a system to do this, because otherwise, if you would lose a substantial amount. You wouldn't be able to get an entire megabyte. So that's why they did this. Why did they not multiply this out to give us an entire 32-bit? I don't know. I personally think that would have been awesome, but maybe at the time memory is just so expensive that they figured nobody would ever do that anyway, or I don't know. But anyway, it does create some interesting situations for you, because let's say that DI is 10. This is going to be in hex, obviously. All this stuff's in hex. So that would give us this memory address, right? Which is identical to this, because this will equal eventually that. Remember, we moved the decimal place over 1, so it'll equal that. And then if we said DI equal to 0, we still end up with this number. So there's a ton of overlapping that you can run across, where this number and this number add together and give you all these combinations that are identical. So just be aware of that. All right, enough of the scaring you away disclaimer stuff. Let's get into it. So the first thing we need to do is we need to set ES somehow to, we're in video mode 3, we need to set it to B800 because that's the segment address that we need to work with. So you might think, oh, that's easy, move into ES, B800, right? Well, let's see what happens. Nope, can't do that. Line number 9 blew up. Invalid operand. You cannot move immediate values into segment registers. Why? I don't know. But they did not give us that ability, so what we have to do is we have to cheat. And the way we do that is we move it into another register that we don't care about. In this case, we don't care about AX because it's done doing its job here, and we haven't set it for its new job yet. And then we can set EX to ES to AX. This is one way to do it. Another way is, in C you have that thing called the stack. So that's another thing we could do. We could also push B800 onto the stack, and then we could pop it back off into ES. And this is another way to do it without contaminating any other registers. So if we were using AX, BX, CX, DX for things, and then we didn't want to dirty any of them, we could do it this way. Another benefit is, look at this. The first way took 43 bytes, the second way took 42 bytes. So we're going to keep doing it this way because when you're working with as little memory as we have, every byte counts, right? Okay. We don't need to worry about using interrupt 10 anymore. We're not going to be using interrupts. We're going to be working directly with memory. Therefore, AH no longer needs to be the 14th. Yes, the 14th function. So SI is going to get us our H. We're still going to use our for loop. Why not? We have it set up to run our 12 times. We're going to load string byte into AL. That still works that way. But let's see here. When we look at our colored text, there's a couple different parts we have to be concerned about. So AL still is going to be our letter that we show on the screen, which is convenient. But AH is going to hold the color we want. Now, the first symbol is going to be the background color. And these are all the colors we have to work with. So you can see there's black, and then there's light black. Oh, sorry, dark gray. Then there's blue, and then there's light blue. And then green and light green, and cyan and light cyan, and red and light red, and magenta and light magenta, and brown and light brown. Oh, I mean yellow. And light gray and really light gray, or white. Basically, yeah. So joking aside, these are your colors you have to work with. And then if you add 8 to that number, which is setting in binary, it is setting the most significant bit. This is the 8th place. So when you set this bit to a 1, it adds 8. And that basically is a brightness bit. It says, take the color I have and make it brighter. That's why I said light black is dark gray and light gray is white and so on. So hopefully that's memorable. In this case, what we want to do is, yeah, why not? Let's use the same type of color. So let's set the background color as white. So we'll set AH to white, which was F, and then let's do green for our foreground color. So we'll do 2. All right, so we should get green on top of white, and then AL is taking care of us using the load string byte. But we still have to move things into the correct memory address. So we'll use store string byte for that. Excuse me. That will move AL into and AH, so our color information and our letter information into the memory location that we want. ES is set, but DI is not. So we need to set DI to 0. So our source index is pointing at our string, and our destination index starts out at 0. Remember, though, we are using this segment to start things out. So let's make this once, and let's run this. Oh, well, that's fancy. Yes, believe it or not, this does make sense. So we did store string byte. And you'll remember that I said, which basically takes the value of AL and it just starts sticking it into the memory. You'll notice that we're missing the letter E, the letter L, the letter O, and the letter L, and the exclamation point. Well, the memory is expecting AH and AL. So instead of store string byte, we're going to do store string word, because we want to store the color attributes and the actual character itself. Let's run that again. Oh, that's special. Okay. So I did not actually expect that because, I'm just kind of speaking off the cuff. So apparently in the BIOS, what will happen is we will get the light green when we set this, but in DOS, it is the blink bit. So it will take green and it will apparently flash it on our screen. Let's make sure that that is true. And instead of setting our... No, we didn't use light green. Well, that is special. There obviously is another flag being set somewhere that says, blink that for me. Let's explore. What happens if we get rid of our F and run this again? We didn't run make, so that would not have actually done anything. Ah, interesting. Okay, so by doing that, I switched it to 7. So in this color chart, you only have, so how do we term this? In the BIOS, these are the colors you have to work with, and the background and the foreground both use the same color information, all of this. In DOS, it does things a little differently, apparently. And if you use these colors, well, you'll notice that I use 7, which happens to still be white. Where's DOS box? So yeah, this is, or I guess it's light gray. If you look at this, it's light gray. If we change it back to F, which was white, what I think we'll end up with is we'll still have light gray, but instead of showing the color white, that bit I told you about, the light color bit, they're using as a blink bit. And yes, it's still light gray. It's not white. So that's cool. A little unexpected, and it makes me want to explore real quick. What happens if we set this to our light gray again, but now we use light green? Will that also blink? No. Okay, so that just gives us burn your eyes out neon green. Cool. And obviously if we did FA, I would assume that we get the super bright green and it would flash on our screen. So let's do that real quick. Yep, perfect. So that's interesting. I actually didn't know about that because I haven't played as much with the DOS versions of this as I have with the BIOS versions, and apparently there are differences. So that's always fun, learning something new. I have read about it before, and I knew in the BIOS it would not blink, so I just disregarded that whole blinking stuff and assumed I wouldn't run across it. But lo and behold, you gotta always read things because you never know when something's gonna come back. Well, that's all that I have for you. I think I've probably taken enough of your day. But if you look at what we've covered today, we have explained how all the memory works. We've gone into hexadecimal, binary, and all that. We talked about what the registers are and how we use them, why we use them. We've refreshed ourselves on bytes and how hexadecimal characters correspond with bytes. Each digit, hexadecimal digit, is a nibble, and then 2 of them is a byte. We have spent some time looking at hex, which is fun, and we've been able to see how these different things work and how our program grows and shrinks accordingly. We discussed what interrupts are. Basically, it's other people's code that we call, and they are numbered. We've explained the memory layout a little bit, the area of memory that we work with, and what origin points do. And then we got into BIOS calls to show that indeed we have the ability to use the BIOS, which if you look at, I don't have DOS programming on here yet, but I plan on adding that eventually. If you look at the DOS services, which are interrupt 21 things, or DOS functions, they're all called interrupt 21. There's a lot of stuff here. You can do all this, but you also have access to all the BIOS stuff as well. So you can see there's a lot of pre-built, quote-unquote, standard library stuff that you can do. So that's exciting. And then we worked with the memory directly. So we got rid of our BIOS calls, we got rid of our DOS calls, and we just worked directly with the memory. Now, we still did have to use the terminate program DOS call, and we had to set up our video mode to support color. And as far as I know, there's not a real easy way to do this other than this way. But I learn new things every day. Obviously, I did with this blinking thing. So I will keep you informed, and as I learn more and more how to get rid of other people's code so that eventually the only code you have to call that's other people's is the return 0 code. Because I think that's neat. I think that's neat that you're talking directly to the computer and you just have a raw piece of crystallized silicon with different doping in it for your p-type and n-type junctions, and you're sending it electrical signals and it's doing everything, and nobody else was involved minus the hundreds of engineers that designed the chip and the miners that mined the silicon and the chemists that converted its structure. But we'll just ignore all of them and pretend that we did all this all by ourselves. There's no other programming involved. It reminds me of that XKCD comic where it said to be a real programmer. It basically gets down to you have to invent the universe. So, but anyway, that's all I really have for you today. I hope you enjoyed this long form format. You probably went through a few drinks by now. But we just kind of leisurely went through. We covered a lot of ground. We showed how the different systems interact with one another. If you saw my first video where I talked about how DOS is basically just a file system built on top of the BIOS, now you know what I was talking about because we're able to use all the fun little BIOS stuff. And then we worked directly with the memory. We even got color and we got blinking. which was a surprise for me too. So I look forward to seeing you in the next video. I doubt they'll be quite this long, but for those of you that enjoy just hanging out and watching code and learning, we are going to make videos for you as well. So we look forward to seeing you next time.